Welcome to the seminar. It's my pleasure to introduce Prof. Sogge from John Hopkins University, who will speak about curvature in harmonic analysis and harmonic analysis on compact.
Okay, thank you. It's nice to be here. Thanks for the organizers. I wish I could be here longer, but it's been a very busy year. So as you can see, this is joint work with a bunch of young people. Xiaoxi Wang at Louisiana State University is a former student of mine. Zhengkai Tao, he's currently a postdoc at IHES. He's a former student of Maciek Zworski from about a year ago, and a current student of mine, Zhijing Zhang at Johns Hopkins. And it's based quite a bit on earlier work, both with Matt Blair and with Steve Zeldich. And it's kind of an update to a talk I gave that one or two of you might have listened to during the Steve Zeldich conference that he tragically passed away at the end of the conference. And I was rushing really hard to do something so I could present it at that conference. And this is an update. So here's the outline. So I write too much on every slide, I apologize. So using classical harmonic analysis and very classical geometry, we'll finally be able to obtain sharp bounds for the size of log quasimodes on compact manifolds. Still have a little bit of jet lag. And these estimates will allow us, the growth rate of quasimodes on compact manifolds of constant sectional curvature will allow us to classify the curvature of the manifolds. So it's a new result. And then we'll be able to extend these estimates for compact manifolds to manifolds of bounded geometry. And using these in quite a bit of existing technology, we'll be able to prove sharp Strickhartz estimates and sharp quasimode estimates on convex co-compact hypersurfaces. So it's first these estimates that don't involve a pressure condition. Okay. The first part is joint work with Xiaoxi Wang. The last part is joint work with all those people I mentioned, all those young people. All right, so let me go over the things we'll study. So we'll study eigenfunctions. So for me, the eigenfunctions are eigenfunctions where lambda is the eigenvalue for the square root of the Laplacian, first order operator. And always assume that the eigenfunctions are L2 normalized. And then if you have a compact manifold, you can expand an L2 function, of course, in terms of its Fourier series, where these are the Fourier coefficients. And a quasimode is just going to be a function whose spectrum is localized to an interval. So our intervals will be of the form lambda, lambda plus delta of lambda. And of course, this means that if you take any of the Fourier coefficients for an eigenvalue outside of the interval, it's 0, okay? And we'll usually take delta to be 1 over log lambda because of the Ehrenfest time. So on manifolds of negative curvature, this is more or less needed. Although in tori, you can get some better estimates than what I'll be presenting, involving smaller windows. Okay, where do we go? All right, so I'll eventually tell you that the estimates we get are sharp on compact space forms. These are compact manifolds where the sectional curvatures are constant. When I say curvature, I mean sectional curvatures. So the model manifold of positive sectional curvature, of course, is a sphere. The model for the model flat case is a torus, and then there's manifolds of negative curvature. So any compact space form with positive curvature is a quotient of the sphere, and any flat compact space form is a quotient of the torus, and then of course any manifold of negative curvature is a quotient of hyperbolic space. So in order to prove that the estimates will eventually, yeah, I know, that we'll eventually state are sharp, we'll need the assumption of constant curvature, and we'll need to know this, use this structure. Sorry about that.
Yeah, is it not usually the case that the word space form is more simply connected?
Oh, these are simply connected. Or no, it's not. These are connected.
I thought space form was simply connected.
No.
Okay.
This is what they call, yeah, so people have studied these quite a bit. What's that? Space form just means, So the space form to me and to geometers just means that it's constant sectional curvature. Okay, and so the space forms of positive curvature are quotients of the spheres. The flat ones are quotients of the torus. So in the positive curvature case, right, you have the sphere, and you also have real projective space. For the flat case, you have tori or Klein bottles and so on. So people have studied these quite a bit. Okay, all right, let's see which. All right, so a long time ago, I was interested in applications to, I was interested in improving results for harmonic analysis on compact manifolds. And I was interested in generalizing something called the restriction theorem for the Fourier transform, if you know what that is. And so I was led to studying the spectral projection operators, where you just project onto a unit band of the spectrum. And I was able to show that the spectral projection operators send L2 to LQ with a growth rate of lambda to a certain power. And I cared about this way back when, because it turns out that the power, if Q is larger than a critical exponent, I'll explain to you why this is critical. The power is exactly what's called the sharp index for Bach-Nuri summability. So I predicted that if you could prove this estimate for this range, you can adapt Charlie Pfefferman's proof that restriction theorems in Euclidean space imply Bach-Nuri's theorem. You could do the same thing for compact manifolds. So eventually that turned out to be correct, but that's why I wanted to prove this estimate. And then I realized that just by interpolating, if you interpolate between the result for this critical exponent and the trivial result for L2, it's a projection operator, so it sends L2 to L2 with norm 1. If you interpolate, you get this behavior for small exponents. And I didn't particularly care about this. But this is the range of exponents that's relevant for the things I'll be talking about today. The harmonic analysis to understand when you can improve these universal estimates for this range of exponents is fairly hard, okay? I showed that if you're only interested in projecting onto a unit band of the spectrum, this is always sharp. It's totally agnostic to any curvature assumptions and so on, okay? This is a very local estimate. It's based on understanding the wave equation for a unit slice of time. So if you want to, if you want to get improvements, for instance, for negative curvature, you're going to be exploiting the fact that the curvature is very chaotic. You won't see that the curvature is chaotic if you're just understanding, if you're just interested, if you just study the wave equation for a unit slice of time. You have to watch the movie for much longer. So if you want to improve this estimate, you have to have intervals that shrink down, that shrink down as lambda increases. And the natural length of the intervals that you might want to consider is 1 over log lambda. Those are the log quasimodes.
And you want exactly 1 over log lambda, or the constant doesn't matter?
The constant doesn't matter for the analysis that I do. Yeah. If you can get it for 1, then you automatically get it for short, smaller intervals, but you'll have the same constant as you would for 1, just because it's a projection operator. But it'd be nice, of course, if you could beat 1 over log lambda. Okay. Let's see. All right, so these are the new results. I've studied this problem for many, many years, and finally, Xiaoxi Wang and I were able to prove the right results. And here's what they say. So if you assume that all the sectional curvatures are non-positive, we're allowing variable curvature, then this turns out to be sharp. So if you take these projecting onto these intervals of length 1 over log lambda, if you assume that the curvatures are non-positive, then the sharp estimate is this, the same powers in the universal bounds, but then you get this improvement, which is log to the minus mu, or mu is the exponent, which is n minus 1 times a half minus 1 over q. Okay, so this is what happens when the curvatures are non-positive. This is sharp for the flat case. If you assume that the curvature is negative, you can do a lot better. You can get an improvement which is like 1 over the square root of log. So if, for instance, q is equal to qc, then q is larger than 2. So that means that 1 over qc, which is this power, is smaller than a half. So this power is always smaller than a half. So this is a stronger estimate than this. Okay? And this estimate is easily seen to be sharp because if you use the Cauchy-Schwarz inequality in a simple argument, you can see that this estimate right here implies the estimates where you project onto unit bands of the spectrum, which is always sharp. So if you had a better estimate than this, you could use it to prove a better estimate for projecting onto unit bands of the spectrum. That's impossible, okay? So this is sort of the what you dream about, is getting this type of improvement, okay? All right, next. All right, so you can use that theorem to hear, this is sort of, you can hear the shapes of manifolds of constant curvature.
Sorry, can I ask a maybe a silly question? Just, there are these conjectures about an infinity knobs having a very good bounce in eigenvalue. And what do you mean by sharp in that sense, that they seem much better than what you're getting? Maybe I'm confusing something.
Well, we're talking, you might be talking about eigenfunctions. I'm talking about quasimodes. So for quasimodes, the estimates that I talked about are sharp, but people expect that if you're just dealing with eigenfunctions, kind of related to her question, then you should be able to do better. But with current technology, that's sort of all you might be able to hope for.
So in the worst case scenario, you will have multiplicity as large as one of as lambda over log lambda, and then you're cooked. It's hard to believe.
Okay, so let me explain why they're sharp if you have constant curvature. So this notation, so you say if f and g are non-negative, you say that f is capital theta of g if the lim sup of the ratio as lambda goes to infinity is between 0 and infinity. So it means two things. It means first that f is big O of g. Can you all see what I'm looking? And it means that the big O statement is sharp. Okay? So if you have constant sectional curvature, it'd be nice to remove the constant curvature, but if you have constant sectional curvature, all this says is that the estimates from the previous slide are sharp. And it's fairly easy to see that the L2 into LQ mapping properties of this projection operator are the same as the supremum of the size of LQ norms of L2 normalized quasimodes. Okay, so you can read off the curvature of compact space forms in terms of the growth rate of L2 normalized quasimodes. If they're growing like lambda to the mu, that's the universal estimate, as I'll tell you in a minute, that's sharp on the sphere, then you're in the positive curvature case. If they're growing like lambda times log lambda, 1 over log lambda to the mu, then you're in the flat case. And if they're growing like this, then you're in the negative curvature case. Okay, so if you like, this is another way of seeing curvature, but it requires constant curvature, okay, in terms of the growth rate of these quasimodes. Okay, now let's talk about early results. So there was a very influential result in the 70s due to Berard, who studied the L infinity estimates, okay? And he showed that for the supernorm estimates, you go from L2 to L infinity with lambda to the correct power, which is n minus 1 over 2, and you get this square root of log improvement. So Berard did that in the 1970s. And then in another influential paper from 2015, Hassel and Tacey showed that if you're larger than this critical exponent, QC is 2 times n plus 1 over n minus 1. If you're strictly larger than the critical exponent, then you always get this wonderful 1 over square root of log improvement for the log quasimodes, okay? So in the earlier slide, I told you that in the cases of constant curvature, there's a difference between the growth rate of quasimodes from the flat case to the negatively curved case. So if you're larger than QC, you don't see that difference. You have the same estimates for the flat case and the negative curvature case. And why is that? Well, if you're dealing with exponents which are larger than this critical exponent, then the types of quasimodes that saturate the estimates are just concentrating at a point. And there's no difference between the way that the quasimodes in the flat cases versus the negative curvature case concentrate at points. Much more subtle thing is what happens at QC or below. So if you're below QC, then the quasimodes that saturate the estimates from a slide ago actually are concentrated near G at Essex, okay? So the way that they concentrate near geodesics is definitely very sensitive to the curvature, as many people in the room know. Okay. All right, so quickly let's go over what happens in the Euclidean case. So this is a equivalent way of formulating the Stein-Thomas Fourier restriction theorem. So it says that if you're dealing with the projection operators in Rn, so there you just take what would be the inverse Fourier, the Fourier's inversion formula, and you just integrate over an annulus where the norm exceeds between lambda and lambda plus delta, so that's a projection operator, of course. Then if you're at QC or larger, and you deal with an annulus, or you deal with projection operator for intervals of length delta, then you get lambda to the correct power mu, and then you get this square root of the length of the interval improvement, okay? This works all the way down to delta equals 0, okay? And this is sharp due to something called the Knapp example in harmonic analysis. And so you can write down a function that saturates this estimate as follows. So the Fourier transform has to live between, in this annulus where norm exceeds between lambda and lambda plus delta, and then you just put inside there the biggest possible rectangle you can. So in the radial direction, of course, it would be size delta, and then to stay in the annulus, in the tangential directions, it'd be this, lambda times delta square root. So you can write down a function like that that saturates these estimates. Okay, and it shows that everything here is sharp. If you want to get this wonderful square root of delta improvement, you need that Q is larger than QC, and so on and so on. And I want to point this out because it was kind of strange to me when we were doing this, that the compact case with negative curvature is actually better than the Euclidean case. So in the case of negative curvature, all the way down to 2, not at 2, of course, you get this 1 over delta, which in our case is 1 over log delta, 1 over log lambda. You get the square root of log improvements all the way down to 2. I didn't say that very well. And you don't for the Rn case. Okay, so that was kind of surprising to me. So so if you have negative curvature, right, there's nowhere that the eigenfunctions or the waves can disperse, but yet you get stronger results for these log quasimodes than you do in Rn. So that was kind of surprising to me. Okay. And so let me quickly tell you what saturates the estimates in the case of positive curvature. Okay, so if you're on the sphere, then the eigenfunctions, of course, are the spherical harmonics. They're the restriction of harmonic homogeneous polynomials to the sphere. So if you're dealing with the n sphere lives in Rn plus 1, and the functions that saturate the LQ estimates for Q at QC or smaller are these guys right here. These are called Gaussian beams. You introduce this factor so that it's essentially L2 normalized. This, of course, is a spherical harmonic, x1 plus I, x2 to the k. It's homogeneous, and it's also awfully harmonic because it's holomorphic. And so this is needed. It's an easy exercise to get the L2 normalization. And it's also an easy, basically middle school exercise to see that this guy right here essentially lives in a 1 over square root of lambda. So lambda and k are related like this, so lambda is basically k. This guy right here is essentially supported in a k to the minus 1/2 or lambda to the minus 1/2 neighborhood of the equator. Away from there, it's just getting exponentially small. So for all practical purposes, this guy right here looks like this normalizing factor times the indicator function of a k to the minus 1/2 or lambda to the minus 1/2 neighborhood of the equator. Of course, the equator is a periodic geodesic. And using that fact, you can see that it saturates all the estimates. And so that's the end of the story on the sphere. If you want to show that the estimates are sharp on manifolds of positive curvature, positive constant curvature, you just use the fact that they're covered by the sphere and do a little bit of work. Okay. Next, the flat case. This was a little bit harder to show that our estimates are sharp, but there was earlier work, actually a lot of work by Germain and Meyerson about getting improved eigenfunction estimates or quasimode estimates for tori. And they generalized the NAP example for Euclidean space to show that on the torus, the estimates that I had stated a while ago are sharp. So their counterexamples work for the torus, and then with a little bit of work, you can show that since any flat manifold compact manifold has to be covered by the torus, you can modify their construction to see that the estimates we obtained are always sharp in the flat case. Okay, and this also is not mysterious to people here, but the funny thing is we can show that our estimates for negative curvature are sharp because if they imply the unit band estimates, which are always sharp, and better estimates for these quasimodes would imply better estimates for the unit projection estimates, which are sharp, but we can't do it directly. So in the case of positive constant curvature or the flat case, I can write down or quasimodes that saturate the estimates, but we don't know how to do this if there's negative curvature. Okay, and of course there's a reason for that. There are no NAP modes that you can write down. I don't think we'll be able to write down if there's negative curvature.
So the equivalent of the Gaussian beams quasimodes, that's a Kanzani-Galkowski defined a few years ago and used to analyze the spectral projector, they wouldn't work.
Negative curvature, you mean?
Yeah, I mean, they use these Gaussian beams type quasimodes in negative curvature to prove precise estimates on the spectral, on the local Weil law. And these examples that they built, I mean, since the philosophy is that they are similar to the Gaussian beams on the sphere.
I kind of doubt it. I'll say, yeah. So actually it's related to this slide. Yeah. So Steve Zeldich and I, a long time ago, were interested in trying to prove partial results to a conjecture of Yau about the size of nodal sets. Nodal sets are the zeros of eigenfunctions. And the existing lower bounds were pretty bad. They're doubly exponential. And we were able to show that they're larger than lambda to some negative power, actually by studying a weird problem where you take the size of L1 normalized quasimodes measured in L2. Oops. And the sharp estimates for L1 versus L2 things, so you L1 normalize the quasimodes and then study the growth rate of the L2 norms, is on the slide. So if they're like lambda to n minus 1 over 4, then these examples show that you have to be positive curvature. If they're lambda over log lambda to n minus 1 over 4, you have to be the sphere, you have to have positive curvature. And then in the case of negative curvature, you can get any negative power of lambda that you want. So I don't know the result. We'll talk about that later on. But the fact that when you compare the L1 versus L2, you can gain any negative power of log lambda tells me that it would be hard to write down NAP type examples which are relevant for the problems I'm talking about.
Okay. So you said this is a corollary of.
Yeah. So it's a corollary of both results. So the upper bounds are just using Holder's inequality and then the LQ estimates. Okay, and the NAP construction tells you that the first two lines are sharp. And of course, there's no.
So you get the arbitrary pen by adjusting the Q.
Yeah. And so it was fun back when we were doing this, but when we proved estimates like this, we could prove new estimates towards Yau's conjecture. It made it easy to write NSF grants during that period of time. But then unfortunately, just a couple months before I was supposed to write a NSF proposal, Lagunov completely solved the problem. So this didn't get you very far, but it was fun. Okay. All right, so let me say a few words about the proof. Okay, not so bad. So let me tell you how to prove the upper bounds, okay? So in harmonic analysis, what you often have to do is you have to know your enemies, right? And then you have to build your arguments around your enemies. Morgan was really good at this. And Hong Wang is good at it too. So in our case, there are two enemies that we have to make sure are not present if you're in the flat case or if you have negative curvature. There's the enemies that exist on the sphere. I already told you about one. Those are the Gaussian beams. Those are relevant for proving estimates. Those are relevant for showing estimates are sharp for relatively small exponents. And there's also zonal eigenfunctions. So zonal eigenfunction will saturate the estimates for Q larger than the critical exponent. And the L2 normalized zonal eigenfunctions look like this. They have size lambda to this power n minus 1 over 2, and they have lots of mass inside of 1 over lambda neighborhoods of the North Pole and the South Pole. Okay, so these will saturate the estimates for large exponents. And then there's the Gaussian beams that we talked about before. They basically look like the indicator functions of these lambda, 1 over square root of lambda neighborhoods of the geodesics. They have that size, and so therefore their LQ norms are like this. So if you want to show that you can beat these estimates when you have non-positive curvature or negative curvature, okay, you have to rule out having log quasimodes that look like these. These are pure eigenfunctions, so they're automatically quasimodes on the sphere. So you have to show these guys can't exist. Okay, so therefore the proof of the positive results kind of splits into 2 steps. The first step is to show that these guys can't exist. And then the hard step that uses quite a bit of harmonic analysis is to show these guys can't exist. Okay, all right, so that's the estimate we want to show. We want to show that you get the correct log improvements if you have non-positive curvature or you have negative curvature. And the strategy is to split our estimate into 2 parts. Recall that the Gaussian beams have this size. They're lambda to the n minus 1 over 4. So you're basically splitting off, estimating the LQ norm of this guy right here in terms of the region when he's strictly bigger than the size of Gaussian beams versus the region where he's basically of the size of Gaussian beams or less. You have to include these extra fudge factors, 1/8, to make things work out. Anything positive would work, okay? And so we just include 1/8 because it works out in all dimensions, okay? And there's been some recent work, by the way, of trying to get improved estimates for eigenfunctions where they have to be more careful about the 1/8 and things like that. But 1/8 will work for what I'm talking about. Okay, and so you split things up into 2 parts. So the first part is basically saying zonal eigenfunctions can't work out. So if you're in the region where the thing you want to estimate is larger than the size of highest weight spherical harmonics or Gaussian beams, then you want to show that actually you get a big improvement. So even in the flat case, you get, in this region, you get 1 over square root of log improvement. So this is a strong estimate. This can't be true over the entire manifold because you can't get this much improvement on the tori, for instance. So it's better than what you would hope for the flat case. And then if you're in the region where there might be Gaussian beams lurking around, you prove the right estimate. So you get the correct improvement in the case of non-positive curvature, and then this 1 over square root of log improvement if you have negative curvature. So these 2 estimates, because this is what you're trying to prove for the entire manifold, these 2 estimates will do it for you, okay? This estimate right here is much harder, and it requires quite a bit of harmonic analysis because this guy right here is sensitive to concentration near geodesics. Well, this estimate up here is only sensitive towards concentration near points, okay? So points aren't very interesting. All right. So the small height region, a large height region. Okay, so large heights, so the first estimate up there, that estimate, which is only seeing concentration near points, is fairly straightforward. How do you do it? Well, first you show that the projection estimates satisfy certain bounds. If you were in Euclidean space, this would be the size of these projection operators. If you're on a manifold of negative curvature, unfortunately, you get this thing that's blowing up as the length of the spectral window decreases, okay? And you can only have spectral windows which are basically they're bigger than 1 over, constant times 1 over log lambda. So this is a very classical estimate. This is implicit in the work of Bayrard and so on. So due to Bayrard, you have this estimate, and if you just use this estimate, that's one of the main things Bayrard used in his proof of the improved Weil laws when there's negative curvature. And this plus an interpolation argument is what Hassel and Tacey used to show that you get this square root log improvements if you're above the critical exponent. Okay, what do we do? Well, lucky for us, in a very famous paper of Bourgain, this was his Kakea paper. So there were two papers that for harmonic analysts put Kakea on the map. There's Charles Pfefferman's ball multiplier paper, which showed that the ball multiplier is only bounded for p equals 2 in higher dimensions, and he constructed his counterexample using Kakea. Bourgain sort of went the other way around. He proved some new Kakea estimates, and he also used these new Kakea estimates to basically prove new Bach-Norris estimates. Everybody knows what the Kakea conjecture is, right? It says that if you have, where's my fountain pen? If you have a unit line segment in every direction, that's a Kakea set. Besakovich shows that there are sets like that are measure 0, and you want to show that the dimension of those Kakea sets is full. It's easy to show in 2D, and Bourgain had some new results in 3 and more dimensions versus the trivial estimates, okay? Okay, so Bourgain wrote his paper. I remember a bunch of us, Mike Chris, Tom Wolfe, and I were just in awe of Bourgain's paper. Very difficult to read. And I already knew how to prove the Stein-Thomas restriction theorem. Stein's my advisor. And so I just ignored that part of the paper. But Tom Wolfe said, did you see Bourgain's proof of Stein-Thomas? It's really cool. And so since Tom Wolfe was recommending that part of the paper, I thought I should read it. Well, using Bourgain's, and this is one of the only times I know in Bourgain papers, a lot of it's when we write papers, we want to help the reader, right? So we have like model arguments. Bourgain's papers really never had a model argument. But in this paper, he did. He was proving new restriction estimates, and they had kind of a model argument, which is a new proof of Stein-Thomas. Well, it turns out that you could take Bourgain's proof of Stein-Thomas and do it on manifolds. You can adapt it so it works on a manifold. So you have to trust me. Using a manifold version of Bourgain's argument, it's not difficult to see that if you have this kernel estimate, then you can prove the A+ estimates. Okay, so it's that estimate that's pretty much due to Bayrard, and this Bourgain argument is like perfect. It allows you to prove this estimate in basically a page. This takes many, many pages, much more complicated.
How do the Kakeas appear here?
What's that?
How do the Kakeas appear in that argument that you mentioned to generalize the manifold? I'm just curious.
Well, so he's proving new estimates for actually what's called the Kakea maximal function. And then he's using those new Kakea maximal estimates to prove new restriction and Bach-Norris estimates. So they don't really appear. This estimate, the argument that I use and that he had in his paper is much softer than that. But it works like a dream for the applications I have in mind. So maybe I told you too much in that story. So here's another story. So here's what you need to do to prove the estimates in the region where there could be Gaussian beams, okay? So if you're estimating, so T lambda is the operator that we're trying to study, and we want to show the remaining estimate would be that in this region where you're relatively small compared to the size of the Gaussian beams, then you can control the LQ norm, okay? And you want to show, maybe I'll go back and show you. You want to show that in this region you have these two estimates, depending on the curvature, is non-positive or strictly negative. Okay, so here you use something called decoupling. It's a variation on decoupling, and something Bourgain was involved with too. So in our case, you want to do decoupling where you decompose the T lambda of F, that's the spectral projection operator acting on F. You decompose it in terms of wave packets. And there's a natural way of doing that, which won't surprise you guys. So you take a net of geodesics, so it's a collection of geodesics where the distance between the geodesics is separated by this fudge factor lambda to the -1/8, and then you localize about the geodesic in the crudest possible way. So you work in a local coordinate chart, and then you have a cutoff function in X as part of the symbol of the pseudo-differential operator, and then you localize along the direction of the geodesic. So if these are the new operators associated to this decomposition, so you have geodesics gamma nu, these localize to these pink type regions, then you have this decoupling estimate. You can control the LQ norm in this region by the little LQ of the LQ norm of the localized estimate of the localized operators. Okay, so you're just localizing to lambda to the -1/8 neighborhoods of geodesics. I point out that if you were on the sphere and you had the Gaussian beams, there'd only be one term here. Okay, so this is a standard thing in harmonic analysis, so decoupling type estimates. The famous decoupling paper of Bourgain and Demeter actually had little L2 instead of little LQ. This type of decoupling was introduced by Wolf. So it's very painful to prove this. It's based on techniques, bilinear techniques that go back to the 90s of Tau, Vargas, and Vega. But once you have this estimate right here, which is hard to appreciate if you're not a harmonic analysis, then you're in business. Because what this estimate does, it decouples things. You're trying to analyze this thing, and because you prove this decoupling thing, it turns out that you only need to really understand one of these operators, okay? And the nice thing is that you remember from a few slides ago, if you consider the kernel of the whole operator, it has this exponentially blowing up factor. It'll turn out, this will be on the next slide, that if you just localize these things to these neighborhoods of geodesics, you actually have wonderful estimates for the kernels of each of these pieces. It doesn't have this blowing up factor. That's why you want to spend pages and pages proving this, even though it's a quite standard thing in harmonic analysis. Yeah. Well, we do because we're dealing with the Laplace, and so it would be the curvature of the level sets of the principal symbol. And in the Euclidean case, you only localize in the Fourier transform variable. You don't need to localize in space, okay? But you do here, okay? And for this part of the argument, it's very important that the principal symbol is invariant under the flow and things like that. But at any rate, it's just a natural variable coefficient version of the usual decoupling of Wolf and Bourgain and Demeter. Okay, so we spend all that time because we realize that if you localize these operators, okay, you have this wonderful estimate. You have pointwise estimates for the kernel, which don't include that blowing up factor for the whole operator. And you'll have to trust me that if you combine that decoupling estimate from the previous slide together with this pointwise estimate, you could use standard interpolation arguments that are used to, for instance, prove the Stein-Thomas restriction theorem to get exactly what you want. So it's kind of standard for a harmonic analyst that if you have the decoupling estimates from the previous slide together with this pointwise estimate, you're good to go. Okay, so it takes a lot of work, but this, nowadays is fairly routine. Okay, so everything works out. So it took, I've been involved with projects like this for a long time, but everything works out because you have this decoupling estimate and you have two estimates for the kernel. If you localize the kernel, you get exactly the same bounds that you would in Euclidean space. While on the other hand, if you don't localize it, you got this headache, which includes this exponentially blowing thing that really has to be there. Okay, so that's why you go through that extra painful step of introducing decoupling to basically erase that exponential factor. Okay, so I hope I gave you some feeling about how this is kind of standard harmonic analysis once you set it up right. All right, so real quick, so now I want to talk about my joint work with Huang, Tao, and Zhang. So we were interested in these convex co-compact hyperbolic surfaces, and able to handle that, we needed to generalize the types of results that we proved earlier for such guys. It turns out it's fairly easy to generalize the results from the previous part of the talk to manifolds of bounded geometry and curvature assumptions. everything that I did for the hard part of the talk was really just in a coordinate patch. So if you have bounded geometry, what does bounded geometry? It means that the injectivity radius of your manifold is positive, and you have uniform bounds for derivatives of the curvature tensor. So the local part of the argument, that was the painful decoupling step, that's just done in a coordinate chart. So if you have some uniform control of the coordinate charts and the way they overlap and things like that, you're good to go. So bounded geometry exactly gives you what you need to be able to carry out the decoupling part, the hard part. The other part of the argument was the kernel estimates. The kernel estimates, you lift things up to the universal cover, and then you just have to count how many terms arise when you lift it up, translates of your fundamental domain. So that used the fact that the injectivity radius of the manifold was positive. Okay, so if you use those two things and you do a little bit of work, you'll see that everything I've been talking about works perfectly well for manifolds with the appropriate curvature assumptions and bounded geometry. So we have the same spectral projection estimates, and then I also did some work with Huang and Blair about Strickhart's estimates. So if you're dealing with Strickhart's estimates, you're trying to prove mixed norm estimates for solutions of Schrödinger equation. And so there's a necessary, this is called the Kiel-Tau condition on the exponents PQ. This notation is you fix T, take the LQ norm, and then you take the LP norm in T of the resulting function. So we were able to, in the case of compact manifold, there's a very nice and classical result, the Berkshire and Svetkov, which says that if you do this on a compact manifold, any compact manifold, if you're localizing to frequencies like lambda, you can only prove Strickhart's estimates for a 1 over lambda interval of time. What do? We just beat Berkshire and Svetkov under curvature assumptions, non-positive curvature, by this log lambda. And these log improvements here and here turn out to be crucial for the types of results I'll tell you in the next slide. So they're minuscule improvements. They're only little log improvements, but they're exactly what the doctor ordered. Okay?
If you have, instead of a derivative of curvature bounded, just the curvature bounded, then it's not enough.
It's not enough. You could probably weaken the non-positive curvature, but if you have little pimples of positive curvature, then you're not saying they're necessarily false, but the methods we use are break down miserably. Okay? All right.
So if for example near that manifold that probably if the original manifold we don't have bound on the derivative of curvature, but we can find the manifold very close in good norm,
Maybe. And we only need finitely many, depending on the dimension, bounded derivatives of the curvature tensor. And there could be cases where you perturb. So, yeah. I don't think, that would be pretty difficult, yeah. We do sort of consider background manifolds. I'll tell you about that in just a second, but it's a different nature than what you're asking about. Sorry. Okay, so this is just saying what I was saying before. The assumption about bounded geometry is exactly what you need to make the harmonic analysis techniques from before work out. All right, so let me tell you about our results. So we proved that if you have one of these convex co-compact hyperbolic surfaces, what are they? They're manifolds of constant curvature -1. They include a compact core where there could be lots of trapped geodesics. And then near infinity, they look like a finite collection of hyperbolic funnels, so half of a hyperbolic cylinder. You could also conceivably have hyperbolic cusps, but it's easy to show that these estimates break down miserably in that case. So you really do need the assumption of positive injectivity radius. Okay, so that's their picture. And so we proved these two estimates. So you can actually, just like in the Euclidean case, you can get, well, better than the Euclidean case for the same range of exponents, or actually this is all exponents, not just the q smaller than qc, but for all exponents you can improve on the unit band result by the length of your window to the 1/2 power, so the optimal improvement. okay, for these types of manifolds. And then you also get nice Strickhart's estimates. So you can deal with unit intervals. And if you assume that the manifold has no resonances at the bottom of the spectrum, and your initial data is perpendicular orthogonal to eigenfunctions, you can actually get global Strickhart's estimates where you do replace 0, 1 by R. Okay, so these are our new estimates. And again, you're better than you are in the Euclidean case if in these manifolds, because even for Q very close to Q2, you get this wonderful square root of delta improvement. So let me explain what we do. So, well, before I explain what we do, I'll come back to that picture. Let me tell you about some early results, because we rely quite a bit on early results. So the results for these types of surfaces from a couple years ago due to Anker, Laguerre, and Germain, and they proved exactly the same results that I had showed you before, but they have a little bit of a loss. They have a lambda to the epsilon loss. We removed that, we obtained the optimal results, and then about 15 years ago, I guess, in 2010, there were Strickhart's estimates of Berg, Guillermo, and Hassel, which were not for these things, but were for manifolds where you assume a pressure condition. But their results included hyperbolic cylinders, and we're going to use that. And they dealt with many other cases too. And so here's what we do. So we just happen to be around at the right place in the right time. And there are basically several types of estimates that you need. So we need the results that we obtain about these minuscule log improvements on manifolds of bounded geometry. And then we need also local smoothing estimates. So what's local smoothing? So if you're in Rn and you take the solution to Schrödinger's equation, of course it's a unitary operator on L2. It's e to the it Laplacian. But if you localize to a compact region of space, you gain half a derivative. So that also works if you're in the, if you have a cutoff to the funnel part of the compact, convex co-compact hyperbolic surfaces. So if you cut off to the funnel region, then Burke, Guillermo, and Hassel showed, showed that if you localize to these funnels, you also get this improvement, this 1 over lambda to the 1/2 if you localize to frequency like lambda. And another thing that we use, which is a very deep theorem, which is due to Bourgain and Dietloff, they showed that if you're on these types of things and you localize to the gnarly region, to the core, then since there are trapped geodesics, you can't get this improvement of 1 over square root of lambda, but you get optimal results, which say that you have to also include this square root of log lambda thing. And also the Strickhart's, as I told you before, Burke, Guillermo, and Hassel showed that if you're in the funnel part of those manifolds, you have the Strickhart's estimates. So if you use these two local smoothing estimates, it turns out that you can glue everything together. And this is an argument that's due to, not due to us, but to Burke, Guillermo, and Hassel. So I'll just go back to the picture and explain what's going on. So we have new Strickhart's estimates. If you're just interested in proving the Strickhart's estimates, we have new Strickhart's estimates in this region, but they're very weak. They're only for intervals of length 1 over lambda times log lambda. So pretty bad estimates here. If you're in these regions, then Burke, Guillermo, and Hassel have the optimal Strickhart's estimates. They can prove that, but only for this part of the manifold. And then you have these L2 estimates, these local smoothing estimates. You have nice local smoothing estimates in this region, in the funnels, gaining 1 over square root of log here, 1 over square root of lambda here, sorry, jet lag still. And then you have the results that are based on the fractal uncertainty principle of Dietloff and Bourgain, which show that you have the optimal but worse estimates where you gain by 1 over square root of lambda times log square root of log lambda here. So it turns out that you can cut and paste, and if you use all the estimates I just said, you can use an argument of Burke, Guillermo, and Hassel to prove these things. So the only thing that was missing, and this was a new, the only thing that was missing because of their argument was these estimates from the previous slide, this thing. So this was the only missing thing. So we were lucky. We knew how to prove that. Yes.
There was some preprint by John Keitel that improved the fractal certainty very.
Yeah. So we can handle more than just these convex, co-compact hyperbolic surfaces. So using his result. Yeah. Okay. And so that's sort of how things go. So using this existing argument from 2010 and the local smoothing estimates, including the local smoothing estimates of John Kai, once you have this blue estimate, you're good to go. Okay. And similar things. We modified the proof of Anker, Lagar, and Germain to show that you also have these. So what you were missing, you also have these estimates. And the only thing you needed was the log improvement. Okay, so we were lucky that all those things existed, and you just needed these kind of modest log improvements. Okay, and it looks like I actually finished on time. Thank you.
Thank you very much. Any questions?
About higher dimension.
Well, we're missing the machine. If the only part of the machine we're missing, which is a big part, is the analog what Borg and DLF did. Yes. So there's versions of the practical uncertainty principle in higher dimensions, but they're not good enough to do the local smoothing.
Even for some examples of manifolds, but not.
Don't know anything. Yeah, we were reading the paper. Yeah. Do you have a question? Sorry.
Is any of this useful for understanding node lines of quasimodes?
No. So you need much better results than these things.
So you can write new MSF lines. Except the MSF doesn't have any money left.
Anyone?
Are you thanking us or the eigenfunctions on that?
What's that?
Are you thanking us or the eigenfunctions for our concentration?
For considering.
That joke.
Thank you very much.